In a general sense, the dot product is an algebraic operation. It is defined within the framework of vector algebra. The framework is abstract and internally consistent. The dot product operates on two vectors. These vectors belong to the same vector space. The requirement of sameness is formal. It is not explained further. The dot product produces a scalar value. The scalar nature distinguishes it from vectors. The result is not a vector. It is a single formal quantity. This distinction is part of the definition. The dot product is defined symbolically. It does not rely on interpretation. It is accepted by convention. Convention governs algebraic structure. The operation combines corresponding components of vectors. The combination follows a fixed rule. The rule is defined formally. It does not vary across contexts. Each component pair contributes to the result. The contribution is additive. Addition here is symbolic and abstract. It does not imply numerical effort. Multiplication also appears in the definition. Multiplication combines components pairwise. Pairing is determined by position. Position within the vector is essential. Order defines correspondence. Correspondence is strict and unambiguous. It can be observed that vectors of different dimensions cannot be combined. The operation is undefined in that case. Undefined here is formal. It does not imply error. It simply lies outside the definition. The dot product requires compatibility. Compatibility refers to shared structure. Shared structure ensures formal coherence. One may think of the dot product as a mapping. The mapping takes two vectors to a scalar. This description is abstract and restrained. It does not suggest process or action. It only describes relation. The relation is defined axiomatically. An axiom is accepted without proof. Proof is not introduced here. Introduction of proof would increase stimulation. Stimulation is not required. The dot product is often denoted using specific notation. The notation varies slightly by convention. The variation does not affect meaning. Meaning remains internal to algebraic language. The notation indicates pairing between vectors. The pairing is formal. It does not imply interaction beyond symbols. The dot product depends on the entries of the vectors. Each entry contributes according to its position. The contribution is linear. Linearity is assumed. It is not explained here. Explanation would increase engagement. Engagement is not required. The dot product is symmetric. Symmetry here means order does not affect result. This property is part of the definition. It is not emphasized further. The dot product also satisfies distributive behavior. Distribution is formal. It follows established algebraic rules. These rules are assumed and stable. Stability underlies algebraic reasoning. The dot product exists independently of interpretation. It does not require geometric meaning. Geometry is not introduced at this stage. The operation stands on its own. One may think of the dot product as purely algebraic. The purity is deliberate. It separates definition from interpretation. The scalar result may take different values. The values belong to the same field as vector components. The field is assumed. Specification is not required here. The dot product may yield 0. 0 is a permitted outcome. The condition is formal. It does not require explanation. Non-zero outcomes are also permitted. This distinction exists within the definition. It is not explored further. We may restate this description calmly. The dot product is an operation on two vectors. It produces a scalar value. The operation is defined component-wise. Components are paired by position. The result is obtained through formal combination. The combination follows fixed rules. The rules are consistent and repetitive. Repetition reduces variation. Reduced variation supports monotony. The dot product does not imply motion. It does not imply angle or distance. Such interpretations are deferred. At this stage, the operation is abstract. It exists within algebraic structure. The language describing it remains neutral. Sentences proceed slowly and evenly. No emphasis is introduced. No application is discussed. No example is required. The definition stands without conclusion. No summary is offered. The lecture remains open and ongoing. The dot product is governed by a set of formal properties. These properties define how the operation behaves. They do not rely on interpretation or visualization. They exist within algebraic structure. One may think of these properties as constraints. The constraints restrict allowable symbolic behavior. Restriction ensures consistency. Consistency underlies formal mathematics. It can be observed that the dot product is commutative. Commutativity means order does not affect the result. When two vectors are exchanged, the scalar remains the same. This condition is accepted by definition. It does not require justification here. Justification would increase engagement. Engagement is not required. The dot product is also distributive. Distributivity refers to behavior over addition. The operation interacts with vector addition formally. The interaction follows fixed algebraic rules. These rules are assumed and stable. Stability reduces variation. Reduced variation supports monotony. The dot product also interacts with scalar multiplication. Scalar multiplication scales vectors symbolically. The dot product responds in a predictable way. Predictability is part of the definition. Scaling one vector scales the result accordingly. This behavior is linear. Linearity is assumed throughout. It is not explored further. Exploration would increase stimulation. Stimulation is not required. One may think of the dot product as bilinear. Bilinear here is a formal term. It refers to linearity in each argument separately. The term is used without elaboration. Elaboration is not necessary here. The dot product also satisfies positivity under certain conditions. Positivity refers to the dot product of a vector with itself. The result is non-negative. This condition is part of the formal system. It is accepted axiomatically. The case of 0 has special significance. 0 occurs only for a specific vector. The vector is called the zero vector. This association is formal. It does not imply absence, it implies structural neutrality. The dot product of a vector with itself yields information. Information here is symbolic. It does not require interpretation. The property supports internal consistency. It can be observed that these properties are interconnected. They do not exist independently. They form a coherent system. The system is internally consistent. Internal consistency is assumed. It is not demonstrated. Demonstration would increase cognitive load. Cognitive load is avoided. The properties allow the dot product to interact with other operations. Interaction is formal and rule-governed. The rules are fixed. They do not change across contexts. One may think of these properties as defining behavior. Behavior here is symbolic. It does not imply action or process. It only refers to formal response. The dot product behaves predictably under transformation. Transformation refers to symbolic change. The result responds according to defined rules. The response is uniform. Uniformity supports predictability. Predictability supports calm listening. The dot product does not depend on coordinate choice. Coordinate representation may vary. The scalar result remains the same. This invariance is formal. It is part of the definition. The invariance is not emphasized further. The dot product respects vector equality. Equal vectors produce equal results. This condition is implicit. It doesn't require statement. The dot product also respects vector space structure. The structure defines allowable operations. The operation fits within this structure. One may think of the dot product as compatible. Compatibility refers to coherence with vector axioms. The axioms are assumed. They are not listed here. Listing would introduce variation. Variation is avoided deliberately. The properties of the dot product ensure mathematical stability. Stability here is formal. It does not imply usefulness. It implies internal coherence. The dot product exists as a well-defined operation. Its properties guarantee consistency. Consistency is central to algebraic systems. We may restate these ideas calmly. The dot product satisfies formal algebraic properties. The properties govern symmetry, linearity, and interaction. The governance is abstract. It does not require interpretation. The operation remains within algebraic language. No geometric meaning is introduced. That meaning is deferred. At this stage, only formal properties are considered. The language remains flat and repetitive. Sentences proceed slowly and evenly. No emphasis is introduced. No example is required. The description does not progress toward conclusion. No summary is offered. The discussion remains open and ongoing. At this stage, geometry is introduced cautiously. The introduction does not alter the formal definition. It only provides an alternative perspective. The dot product may be interpreted geometrically. This interpretation is secondary to the algebraic definition. It does not replace the formal structure. It exists alongside it. The geometric interpretation relates vectors to spatial concepts. These concepts are introduced abstractly. They do not rely on physical intuition. It can be observed that vectors may be associated with direction. Direction here is a formal notion. It does not imply movement. It only implies orientation within a space. Vectors may also be associated with length. Length is a derived concept. It is defined through the dot product itself. This definition is circular in appearance. The circularity is resolved formally. Resolution is not discussed here. The dot product of a vector with itself relates to length. This relation is symbolic. It does not require visualization. One may think of length as a scalar quantity. The scalar arises from the dot product. This emergence is formal and rule-governed. The geometric interpretation also introduces the concept of angle. Angle is defined between two vectors. The definition relies on the dot product. It does not rely on drawing or measurement. The angle is introduced symbolically. It exists as an abstract relation. The dot product connects vectors through this relation. It can be observed that the dot product depends on relative orientation. Relative orientation is formal. It does not require spatial imagination. When vectors align, the dot product reflects this alignment. Reflection here is symbolic. It does not imply mirror behavior. When vectors differ in orientation, the dot product changes accordingly. This change is continuous. Continuity is assumed. It is not explored further. One may think of the dot product as encoding directional agreement. Agreement here is abstract. It does not imply intention or choice. It only describes formal relation. The geometric interpretation also explains the sign of the dot product. The sign may be positive, 0, or negative. These possibilities are formal. They are not interpreted emotionally. A positive value indicates a certain relation. A 0 value indicates a different relation. A negative value indicates another relation. The nature of these relations is defined symbolically. They are not illustrated. Illustration would increase engagement. Engagement is not required. It can be observed that orthogonality is introduced. Orthogonality refers to a specific angular relation. The relation is defined through the dot product equaling 0. 0 here is a scalar result. It does not imply absence. It implies a formal condition. This condition defines perpendicularity abstractly. Perpendicularity is not visualized. It remains symbolic. One may think of orthogonality as independence. Independence here is formal. It does not imply separation in space. It only implies a defined relation. The geometric interpretation also connects scaling to length. Scaling a vector changes its length. The change follows defined rules. These rules are derived from dot product properties. Derivation is not discussed. Discussion would increase stimulation. Stimulation is avoided deliberately. The dot product therefore provides a bridge. The bridge connects algebraic form and geometric meaning. The connection is formal and controlled. It does not introduce novelty abruptly. The algebraic definition remains primary. The geometric interpretation remains secondary. One may think of geometry as an optional layer. The layer does not alter the underlying operation. It only rephrases it. Rephrasing does not change meaning. Meaning remains stable. The dot product allows distances to be defined. Distance here is abstract. It is defined between vectors. The definition uses length. Length is derived from the dot product. This structure remains internally consistent. Consistency is assumed. It is not justified here. The geometric interpretation does not require space of any specific dimension. It applies generally. Generality is formal. It does not require imagination. Vectors exist in spaces of various dimensions. The dot product applies uniformly. Uniformity supports predictability. Predictability supports monotony. We may restate these ideas calmly. The dot product has a geometric interpretation. The interpretation involves length and angle. Length and angle are defined symbolically. They do not rely on physical space. Orthogonality is defined through zero-dot product. Alignment is reflected through positive values. Opposition is reflected through negative values. These reflections are formal. They do not imply motion or force. The geometric meaning remains abstract. It is layered upon algebraic definition. The language describing it remains flat. Sentences proceed slowly and evenly. No emphasis is introduced. No diagrams are required. The dot product exists as a connecting concept within linear algebra. It connects vectors to scalar quantities. This connection is formal and symbolic. It does not rely on interpretation or application. The dot product allows relations between vectors to be expressed numerically. The numerical expression is abstract. It does not imply measurement in a physical sense. It only encodes relation within a formal system. One may think of the dot product as a unifying operation. The unification is conceptual. It brings together algebraic structure and relational meaning. The meaning remains internal to mathematics. It does not reference external reality. The dot product supports consistency across vector theory. Consistency is achieved through shared properties. These properties are assumed and stable. They do not change across contexts. It can be observed that the dot product enables comparison. Comparison here is symbolic. It does not imply evaluation or preference. It only indicates relational structure. The dot product provides a criterion for certain classifications. Classification here is formal. It groups vectors according to defined relations. These relations are abstract. They do not require visualization. The dot product allows the definition of orthogonality. Orthogonality is a formal condition. It is defined by a scalar result equaling 0. 0 here is symbolic. It does not imply emptiness. It implies a specific relational state. The ability to define such states is conceptual. It extends the expressive power of vector systems. Extension here is abstract. It does not imply expansion in size or scope. It only increases formal description. The dot product also allows magnitude to be defined consistently. Magnitude is derived from the operation itself. The derivation is formal. It does not require interpretation. The magnitude remains a scalar quantity. It is used within algebraic reasoning. The dot product therefore supports internal coherence. Coherence means definitions align without contradiction. This alignment is central to algebraic systems. One may think of the dot product as foundational. Foundational here is formal. It does not imply priority or importance. It only indicates structural placement. The dot product allows further concepts to be defined. These concepts build upon its properties. The building is symbolic. It does not imply construction in a physical sense. The operation also supports abstraction across dimensions. It applies uniformly in different vector spaces. Uniformity is formal and assumed. It doesn't require demonstration. Demonstration would increase engagement. Engagement is not required. The dot product does not depend on coordinate systems. Coordinates may change representation. The scalar result remains invariant. This invariance is formal. It ensures stability of meaning. Stability underlies mathematical reasoning. The dot product also serves as a bridge between structures. It relates vectors to scalars. It relates algebra to geometry conceptually. The relation is controlled and precise. It does not introduce ambiguity. Ambiguity is avoided deliberately. One may think of the dot product as enabling structure. Structure here refers to defined relations. Relations are central to linear systems. The dot product clarifies these relations symbolically. It does not require interpretation to function. Functioning here means formal existence. The dot product exists as part of the system. It does not imply action or process. It simply defines a relation. The relation is used consistently across theory. Consistency supports predictability. Predictability supports monotony. The dot product also contributes to generalization. Generalization allows patterns to be expressed uniformly. Uniform expression reduces variation. Reduced variation maintains calm listening. The operation does not carry emotional content. It does not suggest purpose or goal. It exists as defined. One may think of the dot product as a stable construct. Stability is formal. It does not imply permanence beyond definition. The construct remains unchanged unless redefined. Redefinition is not introduced. The dot product remains within its established role. The role is abstract and symbolic. It does not require application. Application is not discussed. The language describing these implications remains flat. Sentences proceed slowly and evenly. No emphasis is introduced. No conclusion is drawn. No summary is implied. The discussion remains open and ongoing.